Welcome to Ask and Learn.
Hi, in this video, we are asked which of the following poset is well-ordered. So, well-ordered set is the set that any non-empty subset of it will have least elements, which in this context mean least in accordance to the relation of the poset, right? It depends on what relation we are talking about. But in general, it means element that has nothing preceding it. So there's no set in A such that set is strictly less than S. Or I should say if set is less than or equal to X, then set must be X itself. Okay, so let's go over this one by one. First, this is well ordered. Why? You could use the fact that in positive integer itself is well ordered under this less than or equal to relation, or you can prove it yourself. I'm gonna show one proof that we can use like for other cases as well. So I'm gonna do it once, and in other cases you can use the same argument. Suppose is not. So suppose it's not well ordered, then there exists at least one subset, we'll call it A, such that A has no least element, right? And but A is not empty, so there is X in A. We know that there is something in A, and X can be least element, and so what does that mean? We will call it X1. We will start a sequence. This implies that there is another element called X2, which is different from X1 in A, such that X2 precedes X1, right? I use less than because we know that they are not equal, and this can go on because X2 again can be least element. That means there is something called X3 less than it, and it go on and on. And this sequence of xn is strictly decreasing, right? It's strictly decreasing by at least 1. So x2 is at least x1 minus 1. But it can be like much more lower. We don't know. But this sequence defined like this will eventually hit 10, right? So this subset A of our like proof that we assume exists will go on and on until it hit 10. And when that happens, we will have a contradiction. Why? Because 10 now acts as the least element, because in the entire poset there's nothing preceding 10 anymore, right? When we hit it, when we show that 10 is in this subset, we get a contradiction because 10 will act as the least element for it, but we assume that it doesn't exist. All right, and so the argument from the start that we suppose that is not well ordered is wrong. So it is in fact well ordered. This is the proof by contradiction. every other cases in this question that is well ordered can be proved in this way. So I will skip the others now because the video will be too long. Okay. Next, this one is not well ordered. Why? Consider this subset. So we just take the whole thing and exclude 0 out of it. This has no least element. Why? You suppose, by contradiction again, suppose there is least element called A over B, then A over B plus 1, which is strictly less than A over B, will also be in the set, right? Because A over B here, both A and B is not 0, because we take 0 out, then A over B plus 1 exists in A as well, and it's strictly less than A over B, so it's a contradiction. No matter what rationale we come up with, we're gonna be able to create another one that is less than that number, so it cannot have any least element, so it's not well ordered. Next, so now it's a rational again, but we have restriction on denominator. It cannot exceed 3, right? And A is just positive integers. This one is actually well ordered. Why? Consider this fact that S, like the entire thing, has least element 1 over 3, right? And it's gonna goes on forever. So any subset A of S must has least element, otherwise we can do the following process. So pick anything in A, right? It's not empty, it exists. We can do one of the two things. Either reduce A by 1, or not by 1, sorry, reduce A or increase B, like one of the two things or two things at once, to create. This is the only way to create C over D such that it is less than A over B, strictly less than, right? From the assumption, like in the first cases, we'll assume that A has no least element. So the only way to create C and C over D would be to do one of the two things or both, right? But this will have limits. So denominator can go up beyond 3, and the number above can go down below 1. So it's gonna start at 1 over 3. Like in the first case, it's gonna, if we keep doing this, eventually we hit 1 over 3 and it will break the argument. So we can prove this with contradiction, and it is well ordered. Okay. Next, last one. So this is negative integer, right? So it's stop at -1, but this one has a different relation. Relation here is greater than or equal to. Think of it as a reverse of the less than or equal to that we usually encounter in this subject. What this means is that now least element becomes or is equivalent to greatest element in our usual sense. So I should put a blanket on this. in the less than or equal to sense, right? We can think of it as like the property will become any subset have the greatest element according to our usual less than or equal to. When we do that, we're gonna see that, oh, the entire set has the greatest element, which is 1. Sorry, minus 1. And so any subset, if we assume that it's not well ordered, we're gonna keep increasing again, right? The argument about the xi. We're gonna keep increasing, and eventually we're gonna hit minus 1, and we can't go on. So the assumption that the set has no greatest element will be false. And that is how we prove it. So this is well ordered. All right. You don't really need to convert this to the greatest element, but you're gonna have to operate on a different kind of relation, and you're gonna be confused sometimes. So this is one way to do it. And that is it for this video. Sorry for the long one. Thank you.